Hi, what I have here on the bench today is a UT61E Plus multimeter. I requested this meter from Banggood a while ago for a review, but it had been out of stock for quite some time now. Now, after waiting patiently for more than a month, it finally arrived. And I'm pretty excited about this review as the UT61E Plus is the redesigned version of the original UT61E that many of you are probably familiar with. This Plus series was actually released by UNI-T not too long ago, just a little before the end of last year. If you are interested in this meter after watching this review, please be sure to check out the product link in the video description below. This meter comes in at just under $90 at the moment, so clearly it is not cheap by any means. But considering this is a 22,000 count true RMS meter, and given that it is made by UNI-T, a fairly well-known brand in the test equipment world, the price in my opinion is certainly reasonable enough. Sure, it is roughly $20 more than the outgoing 61E version, but you always pay a premium for pretty much any new product. For example, when I bought my BK2709B 10 years ago, it was about $110, and now you can get the same multimeter for just around $80. Which is about the same price as this UNI-T UT61E Plus. And of course, the BK2709B is only a 6600 count meter compared to this 22,000 count one. Keep in mind that only the E version is the 22,000 count one, and for B and the D versions, they're both 6,000 counts ones. And by the way, I do have an Anon 870 multimeter coming my way, and that one is a 20,000 count meter, which is closely matching the spec of this UT61E Plus, but comes at only half the price. Be sure to subscribe to my channel so you don't miss that review. I may also do a side-by-side comparison in a later video. Comparing this UT61E Plus versus the old UT61E, the specs are largely the same for the same ranges and the same types of measurements, and in some cases the new meter is slightly better. For instance, the DC measurement between 2.2 volts and 220 volts, the accuracy is at 0.05% plus minus 5 counts versus the 0.1% plus minus 2 counts in the old version. Of course, there are some new features not found in the old version, which I will point them out shortly. But there are a few areas the specs are significantly different that I wanted to point out here. For instance, for the old 61E version, the input impedance is spec'd at 3 gigaohms in the millivolt ranges for both AC and DC voltage measurements. But for the current 61E Plus version, the input impedance dropped in the millivolt ranges for some unknown design considerations. Now, the DC millivolt range only has 1 gigaohm input impedance, although still pretty high, but not as high as a 3 gigaohm input impedance in the original version. And in the AC millivolt range, this figure dropped to 10 megaohm, basically the same input impedance as all the other voltage ranges. In my opinion, this is actually a downgrade in terms of specs for this new meter. Now, at 10 megaohms, this is still fine for most of the cases, but if you wanted to use this meter as a cheap electrometer in situations where high impedance is a must, say you are measuring the input signal from a high impedance source, you will surely be disappointed. Another important thing to note is that the new 61E Plus version is not independently certified, and you won't find a CE or UL marking anywhere on this meter. Although UNI-T does have a certified model, which is the UT161 series. And if I compare the differences between the 61E Plus and the UT161E, the only obvious difference I can see is the included fuses. For the 61E Plus, both the 1 amp and 10 amp fuses are rated for only 240 volts, with a dimension of 6 millimeters in diameter and 25 millimeters in length. Whereas for the 161E, it uses a 600 milliamps, 1000 volts fuse for the low current range, and the fuse is slightly longer, coming at 6 millimeters by 32 millimeters. For the 10 amp range, the fuse is 11 amp, 1000 volt fuse, with a much larger 10 millimeters diameter, and it's at 38 millimeters in length. Okay, so that's enough for the intro, and let's take a closer look at the meter. The UT61E Plus is a standard-sized meter, and you can see that by comparing this side by side to my Kaiweets HT118A, and of course it's a smidge larger than my BK2709B. And I really like the new design of this UT61E. It looks certainly more modern than the outgoing version, and the integrated case certainly has a nice feel in your hands, and it serves as an anti-slip purpose as well. So if you look at the back, we have this cover for the USB communication, and which we'll take a look a little bit later, but this one does come with a USB adapter. You can communicate with your PC software. And we also noticed this tripod mount, which is a little bit unusual. You don't find that on any other multimeters, but presumably you can use that to mount on a suction cup or something like a stand on your workbench if you want to use it that way. And I was just actually looking around, not sure if you can see this. Let me try to zoom in. There's a little speck, actually right now it fell underneath here, but that was actually stuck between the acrylic screen and the display here. Of course, we'll take care of that when we do the teardown, but I'm not sure how that got in. Clearly, when it was assembled, there's probably some dust in the environment. That is just something minor, but nevertheless, it's just something I noticed here. And by the way, this meter uses 4 AAA batteries instead of your standard 2 AA batteries in a lot of the meters. But in my opinion, it's definitely better than the 9 volts. Of course, different people have different opinions on that, but that's just my own opinion. This meter also came with these gold-plated probes, which are certainly nice, but the cabling is just your standard PVC cabling, not anything like silicone, so it's not soft by any means. And also because of the maximum current rating of 20 amps, these cables are relatively thick. So, it gets in your way when you're doing measurement, but there's not too much to complain about. The first minor annoyances I noticed is this range switch. So let me turn it on to see if I can demonstrate that. So once in a while when I turn it on to the first, say, AC voltage range, it gets stuck somewhere between the AC voltage and DC voltage, and I have to wiggle it back. Take a look at here. And same thing for other ranges as well. For example, right now, this millivolt range is actually not latched onto millivolt. I can push it back a little bit, and I'm not sure in reality how much that affects your measurement, but it does give you a little bit of sluggish feel here. Again, you can see that we stuck past that voltage notch here, and I can push it back, so that certainly doesn't give you a lot of a clean feel to this range switch, and you can see that it gets easily stuck between ranges. And unfortunately, the range switch is one of the things you get in contact with this meter, with any multimeter, every day. And so far, the best range switch I have found is in this 2709, and it just gives a very crisp feel to it. And even the Kaiweets 118A I reviewed a while ago, I think that range switch also got it right, and it never get stuck between the ranges. It's very, very crisp. But the range switch on this UT61E has a little bit more to be desired. Now, I don't think this will be a deal breaker, but just something to notice. Is certainly not the smoothest range switch that I have seen in multimeters, and pretty much now every single time I turn, you can see that it gets stuck somewhere, not necessarily on the range itself. Now, I do know the mechanism for this UT61E is slightly different than the other, for example, spring-loaded ball bearing, and this is probably attributed to some of these issues, but nevertheless, something to pay attention to. And I have to say, I really like the display itself a lot, and this is probably by far one of the best displays I have seen in multimeters that I've owned so far. And the video probably doesn't do its justice entirely because of the background glare, but in real life, this display looks very sharp, and in all the operating angles that you typically operate a multimeter at, the display never fades away, and it's certainly very, very sharp. And also the update rate is just about right. It's spec'd at 2 to 3 times per second, and it's closer to 3 times per second. That's actually very nice. While we're in this AC voltage measurement range, let's take a look at the measurement of mains voltage to see how this meter behaves. And no problem, as you can see that the light lit up momentarily. That's to indicate that there's a high voltage present. And the benefit of a 22,000 count meter versus, say, a 6,000 count meter in this case would be that you do have this one extra digit to work with, which comes in handy in a lot of the situations. So, no problem at all. I forgot to mention is that as a secondary function, the AC voltage measurement, you can also measure the frequency of the source. So let me quickly demonstrate that. And you can see here, we have 120 volts, and if I press the Hertz button here, it will show you that it's at 60 Hertz. And of course, you can always do the same measurement using the Hertz function as well. So this would definitely give you one extra digit of accuracy here. So now we're at 59.98 Hertz. And I just checked the footage. It seems that there's a pretty bad glare on the video here, even though from where I'm sitting, I can't see the glare. So for that, I'm going to just change the angle a little bit by propping up the meter with this battery here. Hopefully you will see much better on the video here. So compared with the previous version, this one does have a few new features, and one of which being this low pass filtering capability on your AC measurement mode. And for that, really is just to filter out the noise, and it will come in handy when you are measuring, say, a noisy device like a VFD or something to that nature. And so let's take a quick look here. So actually you are losing some resolution here, and you can see that you only get one digit in the voltage measurement. But you see this indicator here, we're in the low pass mode. So let's give it a quick test. And yep, no problem at all. Of course, you wouldn't see that from mains voltage measurement, but just to show you that we're measuring the voltage in this mode here. Next, let's take a look at the DC range accuracy of this UT61E+. For that, I hooked up my DC voltage standard, the EDC MV216A. And let's change the input 1 volt at a time. 1 volt. It's actually bang on. 2 volts. No problem. 3 volts. Now, because if it's a 22,000 counts meter, you see that we lose a digit. And let's go back and see at what point we make that jump here. So 2 volts, 2.1, 2.2, 2.3. Yep, so that's to be expected. Now let's go back down, 2.2. And you notice that it doesn't jump immediately. That's because there's always some hysteresis built in, and it depends on the algorithm. And you can see that we still didn't jump back yet. At 2 volts, we jumped back. Anyway, so let's keep going. 3 volts, 4, 5, 6, 7, 8, 9, 10. As you can see that the UT61E Plus does meet all its DC specifications with no problem at all, which is to be expected given that it's a UNI-T meter. And I was playing around with the manual ranging capability here, and I noticed some issue I'll show you right here. And as this meter has the range button, so the idea is you can manually set the range by pressing this button. So as you can see, we cycle through different ranges. And if you notice that when I press to the next range, it will show as 9.9 volts instead of 10 volts. Now, this usually is fine if you are, the voltage is actually at the borderline, but right now the voltage is actually at 10 volts bang on. So not entirely sure how the algorithm worked in this meter. But anyway, just to point out here. Another new feature on this UT61E Plus meter, not found in the original meter, is that it has this AC plus DC capability here. So let me demonstrate that to you. Although right now we're just hooking up to a DC input, but you will get an idea. So if I press this select button, you will see that the display alternates between the AC measurement and the DC measurement. This will come in handy when you have a superimposed signal that has an AC component. Now, I would much rather prefer they have a separate display to display these two components separately, but this will nevertheless do the trick. And now let's move on to the millivolt range. And by default, it's measuring the AC millivolt, so let's change it to DC. And I again set the voltage standard to 100 millivolts, and we're showing 100.03. That is definitely well within range, and 200. And because this is a 220 count, I'm pretty sure we cannot go to 300. Yep, we can. So let's see if we can do 210, 220, 230. Nope. So yep, 220 counts. So 220 millivolts, that's the maximum we can display here. And if you recall that the spec says that in the millivolt range, the DC input impedance is 1 gigohm, but the AC millivolt range is only 10 megohm. I just want to kind of verify that because I find it a little bit odd. Now for that, I'm going to use my BK precision meter to just do some sanity check here to make sure that the spec is accurate. Of course, I would expect so, but just to verify. So now we're in DC input mode, so that I would expect we're not going to read anything on this ohm measurement. Yep, and indeed it's showing as infinite because this one simply cannot measure that high of a resistance. Now let's change it to AC mode. So let's see. Yep, indeed we're measuring about 10 megohm. Okay, so that spec is definitely accurate. So just keep in mind, again, this is, in my opinion, a shortcoming of this UT61E Plus, as it's not able to provide that high input impedance in AC millivolt measurement mode. I wanted to demonstrate the AC plus DC measurement a little bit more, and for that I'm going to use this signal generator to generate a DC superimposed on an AC signal. Currently I'm measuring the AC component. As you can see that the RMS output is 2.223 volts, and we're largely agreeing with the signal generator's output. And if we switch to DC measurement, you will see that we are actually measuring the DC component, which is just about 2 volts. And this is where the bar graph comes in handy, because the signal is at 10 Hertz, and you won't be able to see that rapidly changing, but you can see from the bar graph it is flickering, so meaning that it does have this AC component in that measurement signal. In order to see the DC and AC voltage component here, what I can do is, of course, I could always just flick back and forth between these two measurement ranges, but also what you can do is to change it to a AC plus DC measurement mode. So in that case, you will see that these two voltages are rapidly switching back and forth. I think I might have found a slight issue with this UT61E Plus meter, and I'll demonstrate that here. So right now, you see we are at 10 Hertz as we just did before, and everything looks fine. And if I reduce it to 1 Hertz, of course, it started flickering. That's also to be expected, as depends on algorithm, and also the input is really low right now at 1 Hertz. Now, if I switch it to AC measurement, let's take a look at what happens here. And it totally gone haywire. And even though it's not able to measure it, but it keeps beeping. So I'm not entirely sure why that over voltage detection kicked in here. But clearly, this is not the case if you're using, say, another meter like BK precision. So if we switch to the AC measurement, right? So let's just hook that in, and you will see that although probably the reading is not going to be accurate, as we mentioned, it's 1 Hertz. The reading certainly is jumping all over the place, but it doesn't have any issue with that input signal, whereas for this UNI-T UT61E Plus, we are apparently having an issue with the input signal being at this frequency, and for somehow it triggered the overvoltage. Yeah, so that's very interesting. I'm not sure whether or not this can be fixed in firmware, but it's just something to notice. Now let's move to the ohm measurement range, and this is, in my opinion, where this meter shines. And you can see here how fast the auto-ranging really is. And this is actually very important if you are doing ohm measurement a lot. Many of the meters out there, the ohm measurement range is very, very slow. And this one is actually on par, if not slightly better than the BK279B. And that's why I use that BK279B on a daily basis, because the ohm measurement range is super fast. Now, this meter certainly does the same trick as well, which I'm very happy about. And let's take a look at measuring a 100 ohm 0.1% resistor. For that, I'm going to actually zero it out, and it's actually pretty close to zero, but let's just route it out. And I'm going to measure this resistor here, and as you can see, that the result clearly is definitely within spec. Now moving on to continuity test. And as you can see, that is really fast, no problem at all. In fact, it is also a latched output, which is nice. But the LED does lag a little bit behind. Now let's move on to the diode test mode. And for that, I'm going to test a couple of LEDs. So the first one I'm going to test is a red LED. As you can see that we have no problem lighting it up. Now, interestingly, it does beep a little bit. And the forward voltage drop is 1.6 volts, no problem at all. So next I'm going to use a white LED. And let's take another look here. This is a white LED. Yep, it does light up, no problem. But it's unable to show the forward voltage drop, which is interesting, as this meter has 4 AAA batteries. I would imagine it would have no problem measuring this, but clearly it's not able to. Now, this is probably in the spec sheet somewhere, but I just expected that it should be able to measure the white LED voltage drop as well. Now moving on to capacitance. And the first one I'm going to measure is this 10 picofarad capacitor. Now you can see that, of course, we have some residual reading, and I'm going to route it out, but let's first take a look here. So let me hit rel. And it's measuring 15, 16. Now, this is actually going to be pretty hard to measure because of the residual capacitance reading here, but as you can see that we don't have any issue measuring that capacitor, which is good. And the next one we're going to measure is this larger one. This is a 15,000 microfarad capacitor, and which of this one should have no problem measuring. We just want to see how fast or how slow the actual measurement is. So the speed certainly is not fast, but it's largely in line with other meters that I have seen, and no problem at all. And next, I wanted to test out the frequency measurement capability of this UT61E Plus multimeter. For that, I'm outputting a signal from the signal generator at 60 MHz, 2.2 volts RMS. Let me enable the output and hook it on to see what we got here. And it seems that it does take a little bit of time, but eventually it settled at 59.99 megahertz. So that's not a problem at all. And just to prove that we're actually reading the correct signal, let's drop it to 50 megahertz, and we're showing 50 megahertz as well here. So now it does seem that depends on how long the gate is set at this UT61E Plus, and it seems that the measurement is a little bit on the slow side. And one thing to note is that in order to measure the frequency at this high frequency range, the output amplitude has to be significantly higher. So, for example, if I drop it to 1 volt RMS, and we are actually not able to measure the signal, even though the signal is present at its input. So by looking at the product manual, it seems that actually above 40 megahertz, the specification is actually not well defined here. So presumably it needs a significant output voltage from the signal generator. And that is actually unfortunate because by the specification, it appears that this one supports up to 220 megahertz. But in reality, for all intent and purpose, you are not able to measure that if you don't have the sufficient amplitude. And I kind of verified that by outputting a signal from my 8642B at 220 megahertz. And actually, even at output of 20 dBm, I wasn't able to detect anything from this meter. So that is something that you need to be aware of if you intend to use this to measure a higher frequency as a frequency counter, and you certainly realize that the limitation is that the amplitude has to be sufficient for you to be able to detect that signal. What I'm going to do next is to do some current measurement. I'm going to skip the HFE measurement for now, as I do have to swap in a different adapter for that. So let's go to microamp measurement, and we'll swap the leads here. By the way, this meter does not have a warning if you are, for example, in the voltage measurement range while your jack is in the current measurement. Just something to pay attention to, as that could easily ruin your day. Okay, so now let's measure some current here. For that, I'm going to use my 100 microamp current standard I built a while ago, and that should give us an indication at the current reading here. So that's roughly bang on 100 microamp, and of course we can switch to the milliamp range, and we'll see that it's reading 0.102. Actually, that's a little bit off, but according to the spec, the current measurement range has a higher tolerance than the rest of the ranges, so that's probably still within spec, though I have to check. Now let's test out the amp range measurement. For that, I hooked up a power supply that is capable of outputting just above 10 amps. And notice that this meter can actually measure up to 20 amps, but that should give you some idea. And for that, I'm going to ramp up the output current. I'm not going to do the full 10 amps just yet, as I don't want any spark going on here. So now I'm going to turn on the full output. And as you can see that we are measuring that with no problem. Now you do notice that we have this LED light up, warning you that this is a high current situation here. And the next thing I want to look at is this non-contact voltage measurement. Even before this review, I read online and also on Dave Jones' EEV blog video that apparently this meter has some issue with non-contact voltage measurement. So let's take a look for ourselves to see if we can draw any conclusion. For that, I'm having my power outlet here, and let's take a look. So as you can see, here is the NCV measurement sensor area, and it's not very sensitive for sure, but if we turn it, you can see that clearly this side is the live wire that in the bundle here, and we are able to detect that. So to test that further, let me plug in this 2-terminal wire, and this one actually only has live and neutral, and also the braid is kind of side by side so that we can see it more clearly. So on this side, that's clearly live, and you can see that we have no problem detecting it, and on the other side is neutral. So it's actually not giving you a false reading. So this, in my opinion, the manufacturers really try to strike a balance between being oversensitive and also not providing false reading, and that sometimes is very difficult to achieve. But I do tend to agree that this meter probably can be made just a tad bit more sensitive, so that at least it does not give you a false sense of safety if the voltage is present. in that situation. But I cannot fault it too much, as you can see that clearly it gave you a clear indication if the wires are separated here, and you can see which side is live, which side is neutral very, very easily. Whereas for other more sensitive meters, sometimes you cannot tell which side is live, which side is neutral. Now, moving on to an even more controversial topic is probably the inclusion of the HFE or beta measurement of your bipolar transistors. Now, a lot of people would argue that inclusion of this HFE measurement in this class of a meter is really out of touch, as people do this kind of measurement typically do not do any transistor measurement at all. And in fact, nowadays, most people probably don't do that. But as a hobbyist, I happen to work a lot of circuitry with transistors, and I do need to know the beta of transistors that I'm using. So this, in my opinion, the inclusion of that, actually, I don't mind it at all. In fact, by providing this nice adapter, I can actually measure my transistors reliably. And, sometimes you do find those very cheap meters who have the transistor measuring capability, but the sockets included are really flimsy, and you cannot really measure that reliably. Now, that said, I do wish that UNI-T makes this adapter optional, as I assume that this one probably adds a significant cost into the overall package here, so that if a user has a ability to choose whether or not to buy this adapter, and that potentially would drive up the sale of the UNI-T UT61E+. So now let's take some measurements of two transistors, and here I have one NPN that is 3904 and one PNP that is 3906. And I know that these two, I matched them a long time ago to about roughly 10% in terms of their HFEs. So let's take a look here. And for this one, I'm going to plug in the NPN socket. It reads 193, and the other one is a PNP one. I'm going to plug in here. And yet, as you can see, it's 185. So indeed, those are matched to be within 10% of each other. And of course, given the sockets here that you can see, you can also use this to measure surface mount components as well. I'm actually curious to see what this center footprint is for, and it's marked K and C, and not entirely sure, as I don't see any contacts inside the K and C, and also this is just two pins. Now, by measuring these two pins, one is actually connected to the positive of the terminal, one is connected to the negative of the terminal. At first I thought, okay, this might be for capacitor measurement, but with this plugged in, you can see that even if we're in the capacitance measurement mode, first of all, in resistance measurement mode, is showing some reading here, but if you're in capacitance measurement mode, and it's actually not able to measure anything, so not entirely sure what inclusion of that footprint is for. And if you have any idea what that is for, please leave me a comment below. As mentioned earlier, this meter also comes with this USB cable, USB transceiver. You can hook it up so that it can communicate with your PC via the software supplied either by UNI-T or an open source software like SIGROC. And I was hoping to show you guys this in action, but as you see here, I ran into some issue while plugging this into my Linux box. And for some reason, it doesn't recognize this USB dongle. And I'm not entirely sure whether or not it's my Linux system limitation or is this CP210X by Silicon Lab. And nevertheless, the result is a little bit disappointing. And if you have any experience or run into similar problems, please leave a comment below. Now let's move on to the teardown, and I have already taken the back cover up and removed the 4 screws here. Actually, this screw is a little bit interesting. You have 2 black ones at the bottom here, and also you have 2 tiny ones securing the battery holder actually onto the main board. So all 4 screws needs to be removed before you can lift up this cover. And the battery cover with the integrated stand actually is quite nice design, and you do have this rubber bottom so that to prevent it slipping on the surface here. So also this screw is a machine screw, it's captive, so you won't lose it by accident. And the fuses are accessible as well without having to remove the entire back cover. And as you can see here, the inside is actually very, very clean and nicely laid out. The input jacks you can see here are all screwed down, so this definitely increases the reliability of these input jacks. As you can see, all those exposed areas seems to be gold plated, which certainly is a nice touch. And you also can see these are heavily via stitched to presumably reduce the DC impedance. As mentioned earlier, this meter is not independently certified, and I suspect that's largely due to these fuses, the inclusion of the smaller fuses. Now, fuses are by no means cheap, so if they can save a couple bucks here and there, that certainly reduces their overall cost. Now, of course, I don't have access to a UT161 meter, and for those who have one, and if you do know if there's any other differences between the two meters, please also leave a comment below. And also, by the look of it, we do have sufficient input protection here. We have 4 PDCs and 3 MOFs. And towards the middle here, we can see, presumably, this is some kind of clamping circuitry for the input protection. And we can see that this board was specifically spent for UT61E Plus and is made towards the end of last year. Towards the top here, we have this HY2613, which is an LCD controller, and we also have a HC32L130, which is your microcontroller. Towards the bottom here, we have another 14-pin chip, and I'm not entirely sure what that chip is doing here. And up here, we have another 8-pin chip. I'm assuming that is the EEPROM used to store the calibration and other configuration settings of this meter. And towards the top in the middle here, we have this resistive divider, which is a precision resistive divider, and by the look of it, a high voltage cap. And that's pretty much all that is on this side. This is actually a lot of effort to remove this board from this cover here, and there were altogether 9 screws that is at various places to securely mount this board into the case. But I have to take it out because there was something stuck between the LCD and the front cover, as you recall earlier, so I have to take care of that before I put everything back. And as you can see, there really isn't too much going on this side of the board, except there is a DMM chip hidden underneath the LCD here. But in order for me to show you that, I have to desolder this LED, which is mounted onto the LCD and soldered onto the board itself. I'm not going to do that, and you can probably see that in Dave Jones' Teardown if you want to look at that chip, as that's the only thing that is hiding behind the LCD here. And now let's take a closer look at this range switch design. And here we have 2 plastic arms that is pressing against these notches on the side. So that's what gives you that feel when you are turning the switch. Now, because of these notches are not very deep, so you sometimes do get into situations where you are between the switches and it's not able to prop itself into the correct position. But that's just inherent to this design. And I forgot to point out while I was doing the teardown earlier that you can see here we have high voltage isolation cutouts on this side, and also here right next to this trace next to the PDC, and also on the other side right next to the fuse here. And this plastic barrier also serves as a physical barrier between these 2 sections of the board. And here towards this corner, you can see this metal piece that serves as a detector for the non-contact voltage detection. And we can see that the back of the case is shielded via this piece of aluminum, and that's making contact with the main board via this spring contact. And that pretty much concludes the teardown. Besides a few issues we ran into, I think this is still, after all, a pretty good meter, especially it is coming from a relatively well-known brand. Also, that its auto-ranging in all of its ranges are very fast. I'm going to use it as my primary meter for a while and report back if I have anything else to update. Now, I hope you enjoyed the video. If you liked the video, please give it a big thumbs up, remember to share and subscribe. I will catch up with you next time.